this is a proliferation of good cells. If this bad proliferation is dominated by this good proliferation, mathematically we can prove that the solution exists globally in time. That's it. So mathematically we have, I can say, let's say, we have a rather consistent system to describe these dynamics. Now, if we look to the dynamical system, so the autonomous dynamical system, it is easy to see that it has 4 equilibrium states. The first 3 correspond to the vanishing of at least one cellular population, and the last one, this one in blue, is a coexistence equilibrium state, so is an equilibrium in which all populations exist with some densities, and for us it's the more relevant, the more meaningful equilibrium state in this context, in this biological context. So we are interested more in the behavior, stability, and so on of this equilibrium. And we were happy that we had these rich dynamics in the dynamical system, and then we studied the stability. And for all equilibrium states, with the exception of this one, which is always unstable, they have their stable and unstable domains, let's say, and in particular for this one, the one which is more meaningful, more representative in the context, we found that it could present a Hopf bifurcation. I do not know exactly what you know about this, but let's say it's a situation in which there are 2 eigenvalues that are pure imaginary, and in this case we can expect to have a periodic solution with constant oscillations in time that for us would be exactly what we need to describe the chronicity of the disease. So we concentrate now on this equilibrium state. And before performing the simulations to see how the solution behaves, we select 2 parameters, because the model, I jump a little bit here, but the model has several parameters. One is this associated with external factors. Another one, we choose this one because the idea is to choose 2 parameters that have an important role in the stability behavior, but not so important in the existence of the equilibrium. So that's why we select these 2. And it was easy to see that in this region the equilibrium does not exist, so we will not perform the simulations for parameters in this region. In this region too, it exists and is locally asymptotically stable. This means that the solution of the system will approach this equilibrium. And here in this dark gray, the equilibrium is unstable. So in this line separating the 2 regions, we will see this passage from stable to unstable or vice versa, and that's the precise place in the parameter space where we have this bifurcation and they have this oscillating behavior. And in fact, using this as a guide for the simulations, we obtain, in fact, the temporal dynamics of the solution in the macroscopic system, showing that all populations oscillate in time with a certain period in time. We can also talk about another feature that are important, but I will not explain here. But let's say the solution, the model was able to produce also other aspects known from the biology that can be interpreted here from the mathematics of the system, of the setting. And here is the corresponding simulations with the system of PDEs. So we have a 3D picture because we have time as here, but also the activity. So let's say after the mathematical analysis, we were able also to extract from the model this behavior that we want to obtain. And another problem, just to finish, is that what happens if we introduce now the spatial dependence of some populations in order to obtain these patterns, these formations of some patterns in the brain, for example. Okay, this means that we will have a new population, which is a population associated to a chemical substance, is cytokines. When we have, for example, multiple sclerosis, we have this substance in a huge quantity, and what happens? The substance is, for example, here, and these self-reactive cells are attracted by this substance and concentrate here. They are attracted to move. But we have a lot of cytokines because they diffuse in our body. You can have here, there, and so on and so on. And so we have a new equation for the evolution of this substance, and we have also here the self-reactive population depending now on velocity. So we have velocity here and here. And this is the general structure with the new terms, diffusive terms in these two equations. And here we have what we call turning operators. Just to tell you the idea, I think the idea is nice. So we are looking for a very detailed dynamics, and these turning operators are able, with kinetic tools, to describe the possibility of the cells to move by themselves, and also the fact that they are attracted by cytokines with another effect. If I have here many self-reactive cells, the other ones are attracted to come here, but they try to fill the empty space available for them. So we are able to introduce these effects in the detailed dynamics. That's why this is the role of these operators. And doing that, I will jump here to avoid this a little bit technical. So the operators have this role to define these aspects, but then we focus on this equilibrium, which is relevant in the dynamics, and the main idea to see the formation of patterns is to fix this equilibrium state, which should be stable without diffusion, and when we introduce the diffusion, it becomes unstable and introduces this appearance of patterns. Okay, we do this with an asymptotic analysis, with a Fourier expansion of the solution, and so on, but at the end, in fact, we observe mathematically and then with numerical simulations the formation of patterns in the brain. I will show you the picture. This is a representation of the solution, but it's very nice. So here we have space and time. This is a phase diagram for one population, and you see here these let's say lines in yellow with high density of populations, in blue low density. So if you imagine that here is space and time, we have here the density, and the lines in yellow we have high values for densities, in blue low values of densities. If we imagine a 3D picture of this, we will see these kind of things. And in fact, this is a pattern of formation. If we select here a final time, we in fact observe here the pattern with respect to the variable, to the x variable in one dimension, So that's it. I want to show this. Okay, thank you.
Many thanks, Anna, for this very nice, interesting talk with the interplay with biology. Are there any questions or remarks? Nobody? Okay.
Anna, why is the space not important when considering this? Why is the space not important? Because you use the time and the information about the system, the biological?
In the first description, the space is not involved because we have a huge number of cells in our body. We have a general description, and this thing does not depend on the part of the body. But when we want to see the effect of the diffusion of some substances. We need to introduce, and this appears in particular in multiple sclerosis. There are a lot of works also in cancer, because the tumor is localized in space. There are a lot of models, interplay between biologists, mathematicians, and this appearance of patterns is important. It's nice from the mathematical point of view, but also important in terms of the disease.
Any other question or remarks? Okay.
Thank you for your nice talk. I will ask, when the solution doesn't exist, or we have the system is unstable, or we have bifurcation, I think it will be nice to look for a control of the system. Control of the system, how to control your system here.
Yes, this is what is done in the task when we introduce a therapy, an external medical therapy to control the developing of the disease. We have introduced this and looking for optimal treatments from the point of view of biology, but this is a control of the system. In that case, in our project, we have introduced a population representing the external inlet of medicine, and the role of this is to stop or to control the proliferation of cells, and we obtain a control of the solution. A bang-bang, in our case, we have used Pontiagrin theory, we had a linear control. I do not know exactly which kind of information do you want to obtain, but it is possible. It could be associated to a treatment, explained from this side, and in fact we observe this on the solution. It stops. But another problem that is very nice, I'm sorry to jump from your question to another point, is the blow-up of the solution. In this case, perhaps has no interpretation, but for example, in the domain of cancer, it could be interpreted as a very limiting situation. But from the mathematical point of view, it's very nice to understand under which conditions on the parameters we can have solution, and this is not so complex problem, but the opposite to study under which conditions the solution blows up from the mathematical point of view is not so easy. We can observe this numerically, but then the exact conditions to produce blow up is not so easy.
Thank you. I think that you say that we have it really, but to modelize to control the system, it will be.
Yes.
Thank you. Thank you so much.
Okay, thanks again. Another time for you, the speaker. And next. for connection, so sorry for this inconvenience. Okay. Well, everything works. Next speaker is Professor Marina Murillo from Cadis University, and the title is Strongly OLP Well Posed for Abstract Time Fractional Moore-Gibson-Thomson Type Equations, please.
Thank you very much. First, I want to thank the organizers for inviting me to give this talk. I'm going to talk about the strongly LP well-posedness for abstract time fractional Moore-Gibson-Thomson equations, and this is a joint work with Professors Edgardo Alvarez and Carlos Vizcarra. Well, I will first start motivating the PDEs, the models we are going to deal with. Later, I will state the main problem we are going to solve, which is the analysis of well-posedness for these abstract fractional Moore-Gibson-Thomson equations, and I will need to recall some basic notions and preliminaries for providing our characterization, okay? And later we will analyze some application and consequences of our characterization. Well, fractional generalizations of heat flux law have appeared when interpolating between the properties of the two flux laws. For example, Comte and Metzler in 1997 proposed a time fractional heat flux law given by this equation, where here we have two fractional derivatives, where the choice of the parameters of the order of the fractional derivatives depend on the diffusion process it's being developed and the complex media where it's being developed. Okay, so here we have Q that represent the heat flux and theta the temperature. In this case, the derivative they consider was the Riemann-Liouville fractional derivative. Considering this time fractional heat flux law, for example, for the choice of alpha 1 and alpha 2 equal to alpha and alpha minus 1, the previous equation, the previous model, is reduced to equation 2. This flux law is motivated by non-local transport theory with memory. That is when there exists a non-local relation between the flux Q and the temperature under this relation, where L is the so-called kernel that depends on the media where the diffusion process happens. Considering this fractional time flux law, recently Kaltenbacher and Nikolic obtained time fractional Moore-Gibson-Thomson equations. Forgetting the nonlinear effects, they obtain these equations, and in this case, they consider fractional derivative in the sense of Caputo. I would like to mention that the classical Moore-Gibson-Thomson equation is an important equation in physics, in thermoelastic theory, and it has been widely studied. So this appeared for the first time recently, and we are going to analyze when this equation has solution and when this solution is unique. So the problem we are going to solve is the following. Given X, a Banach space, we are going to characterize well-posedness in Lebesgue LP spaces from the interval 0 to pi into X. We are going to look for periodic solutions of this equation. So first, the time variable will belong to the interval 0 to pi, and depending on the choice of the parameters alpha 1 and alpha 2 in the fractional heat flux law, we have different fractional Moore-Gibson-Thomson equation. Here we have the so-called type 2, and we will also analyze the same problem for type 1. As you can see, the unique difference between these two models relies in the last term. Okay? Here, A will denote any closed linear operator defined on the Banach space X, and the alpha the fractional derivative we are going to consider is the Liouville-Grunwald fractional derivative. Why have we considered this fractional derivative and not other? Mainly because it preserves periodicity, and it has been widely used, for example, in physics for studying fractional fields at a positive temperature, where fractional oscillators are replaced by thermal fractional oscillator. And it has been also considered in approximation theory, for example, of periodic functions by trigonometric polynomials. Here you have some authors who have considered this fractional derivative in different contexts. So, the main features of this talk are the following. We are going to obtain a complete characterization of well-posedness in LP spaces for these two models. We are going to compare the characterization and consequences of these two models. And I would like to mention that our results are general enough not to require any additional assumption on the operator A, such as, for example, being the generator of a set group. Moreover, our characterization allows, for example, to obtain a well-posedness result in the case A, for example, is the Dirichlet Laplacian in an appropriate domain. Some basic notions or tools that we will need for obtaining our characterization. If X and Y are Banach spaces, we will denote B from X into Y the space of bounded linear operators. If the initial and final space are equal to X, then we will simply denote it as B of X. The LP space from the interval 0 to pi into X will denote the space of all 2p periodic Wagner measurable X-valued function, such that the function restricted to the interval is P integrable. In the case P is equal to infinity, this space corresponds to the space of essentially bounded functions. This is some notation, okay? If ik power 2 alpha is this expression, then ak will be the inverse of this quantity for k equal to different to 0, and a0 is equal to 1. Then the Fourier coefficients of any function f in LP will be denoted in this way and are equal to 1 over 2 pi multiplied by the integral in the interval of the corresponding exponential function multiplied by f. With this in mind, we can define the first notion of being an LP-LP multiplier. That will be an essential tool for providing our first characterization. Given P from 1 to infinity, we will say that a sequence of operators mk is an LP-LP multiplier if for any function f in LP with values in x, there exists another function u in LP with values in y, such that each k Fourier coefficient of u can be defined as the k operator of the sequence acting over the k Fourier coefficient of f. The idea is that we can, for any function f in LP, we can find another function u in LP whose Fourier transform is defined in terms of the sequence acting over the Fourier transform of f. Another important notion is the concept of R-boundedness. Given x and y Banach spaces, we will say that a set of operators in B from x into y are bounded if there exists a positive constant C, such that the R norm of any n-tuple of operators T1, Tn in the set, and any n-tuple of vectors x1, xn in the space X, is bounded by the constant positive C and the R norm of the n-tuple of vectors. This R norm is defined in this way as an average of the norm, but the important point is that when we are dealing and working with Hilbert spaces, this concept is the same as being norm-bounded, which is much easier to be checked. Okay, so here you have the formal definition of the alpha Liouville-Grunwald fractional derivative of any function u in a subspace of LP that I will later define. And as you can see, this fractional derivative can be defined as a series in terms of the Fourier coefficients of u. The H alpha P space is the vector-valued fractional Sobolev space of functions u in LP, such that there exists another function b in LP whose Fourier coefficients are defined in this way, as the power alpha of ik multiplied by the Fourier coefficient of u. In the case alpha equal to 0, this space coincides with the classical LP space. So, let's go to our first model, to the abstract fractional Murchison-Thompson equation of type 2. And when we will say that a function u is a strong LP solution of this model. Well, a function u is called a strong LP solution if u is, of course, a solution and belongs to the so-called maximal regularity space, where this regularity is asked in terms of the Fourier transform. That is, this space is the intersection of the h power to alpha plus 2p space with value in x and h alpha p space with values in the domain of A. One can easily check that if a function is a strong LP solution, then it verifies periodic initial conditions. That is, u in 0 is equal to u into pi, and the same happens with the first and the alpha plus 1 derivative. We must observe that when alpha is equal to 1, we recover the maximal regularity space of the classical Murchison-Thompson equation, because all these fractional models, when alpha is equal to 1, are reduced to the classical Murchison-Thompson equation. Okay, this equation was studied in 2013 by Poblete and Poff. One can see that, in fact, this maximal regularity space is equal to this space, but the most important point is that it's a Banach space when endowed with this norm. That will play a key role in our characterization. Finally, we can formally define what well-posedness means. We will say that the problem is strongly LP well-posed if for any function f in LP, there exists a unique strong LP solution of the equation. So, we can provide our first characterization in terms of LP multipliers. If X is a UMD space, I want to say that UMD space is a subclass in the class of Banach spaces, but we need this restriction because we apply, I'm not going to enter in the details of the proof, but we apply some results that relate the concept of LP multipliers and our boundedness. And in one direction, we need the restriction on X to be a UMD space. In our context, in our work, it won't be a real restriction because most of the Banach spaces we are going to work with are UMD. For example, Hilbert spaces or big LP spaces are UMD. Okay? Then also A will be a closed linear operator, and then we can prove that our equation is strongly LP well-posed if and only if this sequence of operators is an LP multiplier. How does this magical sequence appear? Well, the idea is that if you have a PDE and then you apply Fourier transform, if you solve this equation in terms of the Fourier transform, the solution is defined in terms of this sequence and the Fourier transform of f. And this sequence is usually called the symbol of the equation. Okay? The point is that checking that a certain sequence of operator is an LP multiplier is not an easy task. So we go a step further and we obtain a characterization in terms of our boundedness. Under the same assumptions, we can prove that our equation will be strongly LP well-posed if and only if a certain sequence of elements is contained in the resolvent of the operator A, then this inverse operator is well-defined, and the equation will be strongly LP well-posed if and only if this sequence of operator is R-bounded. I recall that if we are dealing with Hilbert spaces, it's the same as asking this is norm-bounded. Okay, so this is easy to check. Well, an important point or remark is that if one of the previous assertions holds, we can obtain from the closed graph theorem some estimates on the norm of the solution that are very important, for example, when later applying numerical analysis or numerical methods. It's sometimes even more important than the proper characterization by itself. So we deduce that there exists a positive constant C independent of F such that this estimate holds. Okay? Some application and consequences of this characterization is the following. As we have just seen in the previous theorem, the model is structurally characterized by these elements decay. So a simple computation shows that the real part of decay is always negative, and moreover, the imaginary part of decay is always non-zero for each k different to 0. Moreover, well, therefore, the argument of decay is always strictly less than pi, And moreover, we know some information about the asymptotic behavior of this quantity. Here you have, for some choice of the parameter of the equation, the points decay that rely on this continuous line, and we can simply see with this graph that we cannot expect to admit a sectorial operator that admits well-posedness for this model. But an immediate consequence, we obtain the following result. If A is a self-adjoint operator defined on a Hilbert space, and 0 belongs to the resolvent of A, that is A is invertible, then our equation will be strongly LP well-posed. This can be easily checked because the resolvent is contained in the spectrum is contained in the real axis. Okay, and as a consequence, we obtain results, positive results of well-posedness for the Dirichlet Laplacian in bounded domain omega with boundary of C2 class. Okay? We can perform a similar or analogous study for the abstract fractional Murchison-Thompson equation of type 1. As I mentioned before, this model is similar to the previous one except for this last term. So the maximal regularity space changed. In this case, we will say that a function U is called a strong LP solution if it belongs to the new maximal regularity space. This is equal, and this changed because of the last term of the equation. And again, we have that if a function is a strong LP solution, it verifies some periodic initial conditions. Okay? Again, we will say that the equation is strongly LP well-posed if for any function f in LP, there exists a unique strong LP solution of the equation. Okay, we obtain a similar characterization in terms of LP multiplier, where the symbol sequence is given by R, by this sequence, and we can also obtain some estimates on the norm of the solution. Okay? We also obtain an easier characterization, but in terms of R boundedness, and now the model will be structurally characterized by these elements. So if we perform an analogous study, we see some difference between this model and the type 2 model. Observe that here, a computation shows that the imaginary part, again, of decay is always non-zero, and also we can check that the real part of these elements is always negative if this condition holds. If the parameter alpha is restricted to the interval 1/2 and 1, and this quantity is less than 0. Okay? Again, we know some information about this asymptotic behavior, and in the case alpha equal to 1, this asymptotic behavior coincides with the asymptotic behavior of the type 2 model because both are reduced to the classical Murchison-Thompson equation. From this information, we can see that the behavior of this model is clearly different to the previous one, and sectorial operators of a fixed angle theta less than pi can be admitted to preserve or to have well-posedness for this model. I'm not going to enter in the formal definition of a sectorial operator, but the idea is that the spectrum of the operator is contained in the complementary of a sector of the plane, and in this sector, the resolvent operator is bounded. Okay? So, well, here, before we state our main consequences, we have these two pictures. In the first one, we have a choice of parameter where L is negative, and here another choice of the parameter where L is positive. These two figures shows that the condition, the previous condition 7, is a sufficient but not necessary condition to have real part of decay strictly less than 0. Moreover, okay, here we have another choice of parameter where L is positive, but we show that the condition 7 with this picture may fail to have real part of decay less than 0. With this in mind, we obtain again as a consequence that we can obtain well-posedness in the case of self-adjoint operators on Hilbert spaces, invertible self-adjoint operators on Hilbert spaces, but also we have results of well-posedness for sectorial operators. If theta star is the supremum of the argument of decay, that of course the supremum could depend on the parameters alpha, tau, c, and delta of the equation. From the above and the previous analysis, we can see that this supremum for some choice of the parameters can be less than pi. And as an immediate consequence, I'm going to go directly for sectorial operators. The previous result was more general. Okay, we have that if X is a UMD space, minus A is a sectorial operator, okay, with angle in this interval, then the equation will be also strongly LP well posed whenever 0 is in the resolute. This is a condition that we need. Well, all this study can be done for all the fractional version of the Moore-Gibson-Thomson equation. There exist another types, for example, the type 3 model, but in our work, okay, we did not provide a characterization for each model. We consider a general model given by this one in terms of two parameters alpha in the interval 0,1 and beta in the interval 0,2, and for different choices of this parameter, we recover all the type fractional Moore-Gibson-Thomson equations. So we obtain a general characterization and the other characterizations as a consequences, as an application of our main result. Well, if you are interested or if you want to see some more information about this work, it was published in Journal of Differential Equation recently, and here you have some more references on the topic. I would like to especially mention the work by Kaltenbacher and Nikolic, where they introduced these fractional time Moore-Gibson-Thomson equations for the first time. And thank you very much for your attention.
Thank you, Marina, for your nice talk. And we have time for questions.
Are you considering concrete operator A's, concrete examples, like integral operators, for instance? Instead of A, if you take some known convolution operator, some kind of fractional integral differential equations. Are you considering that?
Are you asking me about the operator A?
Yeah.
We consider, or we provide the results for any closed linear operator, and as a consequence, we have results for sectorial, for self-adjoint, and then, for example, for the Dirichlet Laplacian, but not others.
But I mean, for some concrete cases, there are some theory of fractional integral differential equations. So could be some concrete examples, probably.
As far as I know, and for this concrete equation, it makes sense for the Dirichlet Laplacian.
Okay. Yeah.
I mean, in the motivation of this equation is with a concrete operator, the Dirichlet Laplacian.
Yeah,
so we were looking for that.
I mean, for examples, concrete examples.
No.
Thank you for your nice talk. I would like to ask about the LP. The space LP.
Yeah.
Our results are true for all P or?
From 1 to infinity without including infinity.
Without including infinity. Yeah. And for other space?
No. This would be another work. I mean, for example, now we are working we are studying well-posedness in Helder spaces. But for example, in Helder spaces, we need to consider another fractional derivative because this fractional derivative does not make sense in Helder spaces. But this is another work. Yeah. This work is just for, and these techniques are only valid for LP spaces.
LP from 1 to MFT, not including MFT. And there are examples to see that your technique doesn't work for the other space?
No.
No example? Thank you.
Okay, so actually your results work for UMD space, right?
Yeah.
UMD space. So can you just briefly explain where to use this UMD condition?
Yes, when we are, we obtain two characterizations, one in terms of our boundedness and one in terms of LP multiplier. If you have an LP multiplier, then a sequence of operator which is an LP multiplier automatically is R-bounded. But if it is R-bounded and another sequence of operator is R-bounded, then it is also an LP multiplier. But this is only valid for UMD spaces.
Yeah, but I know the R-boundedness may require the UMD property, right? So for the last two results, you didn't mention the R-boundedness because that operator is not a multiplier. Because I think the last two results you represented, you only say, okay, it's well posed, but you didn't say anything about the R-boundedness, right?
Which result?
Yeah, for example, so like this, so there's nothing related to R-boundedness here?
No, okay, they are different conditions. I mean, for obtaining the main result in the proof of these two characterizations for the proof, but I'm not going to enter in the details of the proof because if not, I will be here until Friday. We need this restriction for obtaining this equivalence. That's why in the general results, in the corollaries, we need the space X to be UMD. And inside this proof, again, we need UMD when obtaining the fact that LP multiplier, the truth is that for one of these characterizations, we don't need UMD. It's sufficient if it's a Banach space, that's true. And for the other, we need UMD. But for not entering in so many details, we wrote UMD for both, but yes, it's true. Yeah, you are right.
You.
Yeah.
Are there any other question or comments? If not, we thank again Marina. Okay, next talk is by Benjo Zhang from University of Memphis, USA, and the title is Banach Spaces with Ball Covering Property.
Okay, thank you for the introduction and also thank the organizers for the invitation to this beautiful place and a wonderful conference. So today I'm going to talk about the Banach spaces with the ball covering property. So the ball covering property was first studied by geometers for finite dimensional spaces, and then extended to infinite dimensional spaces by functional analysts. So, so this property is a geometric property, but very closely related to the topological property of the dual space. So let's look at the definition. So take an infinite dimensional Banach space X, and if you look at the unit sphere of the space, and if you can cover the unit sphere by countably many balls, of course not containing the origin, then we say the Banach space has the ball covering property, okay? So if you have a uniform control of the radii of the covering balls, then we say the space has the strong ball covering property. And the covering balls may approach the origin, okay? So if the balls can be chosen so that they are uniformly away from the origin, then the space is said to have the uniform ball covering property. Okay. All right, so of course it follows easily from the definition, every separable Banach space has all these properties, okay? So you just choose the dense subset of the unit sphere, okay? Any balls of any small positive radius would cover the unit sphere. Okay. So the first important results about the ball covering property is proven by Chen. It says if X has the ball covering property, then the dual space is weak-star separable. Okay. So a natural question is what about converse? Okay, if you add some additional conditions, say if X is locally uniformly convex and the unit ball is weak star separable for X star, then X has the ball covering property. And also if X smooth and the ball of X star is weak star separable, you can also get X has the ball covering property. So for those results, you certainly need to add more conditions. And so the real question is still, does the weak star separability of X star implies BCP? Okay, so the following result is actually a renorming result, but it shows you that the answer to the question is no. Okay, let's look at the theorem. So if you choose any lambda between 0 and 1, then you have a renorming of little l infinity in the following way. So the first part is just the original L infinity norm, and the second part is actually the quotient norm, okay? So it's the nim-sup of the coordinates. And this lambda controls the percentage of these two norms. And if lambda is greater than, strictly greater than 1/2, then this new norm would give you the BCP space. But if lambda less than or equal to 1/2, then the new norm gives a space without the BCP. Well, so this result actually tells you that the BCP is not preserved under linear isomorphisms. However, the weak star separability is a topological condition, so it's invariant under linear isomorphisms. So this would tell you actually the answer is no, because the weak star separability is a topological property, but the BCP actually changes when you choose a different renorm, okay? Because you choose a different lambda, choose a lambda greater than 1/2 or lambda less than 1/2. One norm has the BCP, but the other one doesn't have. So this shows you actually the answer for this question is no. All right. Okay, so, and also the result tells you that this BCP does not pass to quotient spaces, because if you look at this result, if we take lambda to be 0, if lambda is 0, then this norm is actually just this part, the nim-sup of the coordinates, which is just the quotient norm over C0. So by this theorem, we can also get that this space L infinity over C0 does not have the ball covering property. So the ball covering property does not pass to quotient spaces. So a natural question is whether the ball covering property passes to subspaces. And another result shows that this little L1, 0, 1, this is a unit interval, which is a subspace of L infinity, which does not have the ball covering property, but it is easy to see little L infinity has the ball covering property. Okay, so it does not pass to subspace. Okay, so although the weak star separability of X star does not tell you the BCP of X, however, they're very closely related. The result, here is the result. If X star is weak star separable, then you can have a it's a renorming which arbitrarily close to the original norm, so that the new norm, under the new norm, the Banach space indeed has the BCP, okay? By a small perturbation, the space can be made to have the BCP if X star is weak star separable. However, this theorem doesn't have a control of the radius of this covering balls. Another strengthened result by Van Zankel tells you that actually, by a small perturbation of the norm, you can get the strong BCP, which tells you that the radii of the covering balls are uniformly bounded, okay? You have an even stronger result, okay? Stronger result. So this tells you the weak star separability actually very close to the BCP, And another result of Van Zankel in the same paper tells you that if you add a slightly stronger condition, that is X star has a countable R norming set, then it can be renormed to have the uniform BCP. Okay, and it follows from these two results, actually the strong BCP and the uniform BCP are different properties in general, because this condition contains a countable R norming set is strictly stronger than the weak star separability of X star, because the count example is just the Johnson-Lindenstrauss space. Okay, Johnson-Lindenstrauss space. All right. But if the Banach space has the strong ball covering property with a very good control, if the supremum of the covering balls, the radii of the covering balls is strictly less than 1, then this forces the space to be separable. Okay? So if the balls can be made very small with radius less than 1, then this would conclude the X is a separable. Actually, this number 1 is the best, because if you look at L infinity, you can choose a countable set of balls with radius 1, exactly 1, which covers the unit sphere of L infinity. So this result cannot be made better. Okay, the best result. Okay, so of course, the first question about these three properties of BCP, strong BCP and uniform BCP, is that whether there are different properties. Okay, in a paper with a law, we actually had a very explicit construction by taking L infinity direct sums of a sequence of spaces with the ball covering property. We showed that the three properties are actually different properties. All right. Another natural question for Banach analysis is the following. If you have two spaces with property P, so you look at the direct sum, whether the direct sum has the same property, okay? So this question was first studied by I'm sorry, I didn't put the name here. So with some additional condition, if the spaces Godot differentiable and both spaces have the ball covering property, then the sum has the ball covering property. And later on with law, we are able to remove this differentiability assumption. Actually, we prove a stronger condition, a stronger result, that is even for the infinite direct sum, the BCP is still preserved. Okay, so if you take a sequence of Banach spaces with the ball covering property, then take the LP direct sum of the spaces, then the direct sum has the ball covering property. This include both 1 and infinity. And of course, the corollary is that if X has the ball covering property, then LP of X has the ball covering property. So what is the next natural question? This is little LP, then what about capital LP, okay? Okay, so the question is, if you have a measurable space and look at LP of X, capital LP of X, if X has the ball covering property, thus LP of X has the ball covering property. But of course, you do have to pose a restriction on the measured space. It can't be too big, because this is a countable covering, okay? It can't be too big. So if you assume the measured space is separable, then the result tells you that this is indeed true. So LP of X has the BCP if and only if X has a BCP. But in this case, there's a slight difference here. The infinity case is not included. For little LP case, the infinity case is included, but here, for capital LP, this is not true. Actually, we actually showed that just capital L infinity itself fails the ball covering property. So actually, infinity is not true for capital LP case. This also provides another proof about the BCP, which is not preserved under linear isomorphisms, because little L infinity is isomorphic to capital L infinity. However, little L infinity has a ball covering property, but capital L infinity doesn't have it. Okay, so this is a simpler proof, okay, than the abstract proof in the earlier papers. All right, so what's next? Little LP, capital LP, then C of K. So let's look at C of K spaces. Okay, so the natural question is, okay, so we do need to find the right topological property about this, say, underlying space K, so that if X has the BCP, then CK of X has the BCP. So in the beginning, the natural guess would be if the topological space K has a countable basis, the second countable has a countable basis. However, we worked for quite some time. We found out there's always something missing there. We can't prove it. Okay? It turns out the right condition is a condition very closely related to a countable basis. This is called the weak basis, the pi basis. The pi base is just a collection of open sets, so that every open set contains one of the elements. Okay? So this is a weak basis, but not basis. Okay, the right formulation is if K has a countable weak basis, then X has the Ball covering property if and only if CK of X has the Ball covering property. So here's the result. So let K be a locally compact Hausdorff space and X be a Banach space. So C0 of Kx has the Ball covering property if and only if both C of K and X have the Ball covering property, or K has a countable pi basis and X has the Ball covering property. Okay? So along this line, we actually go from the finite direction to infinite direction. So little LP case, capital LP case, C of K case, and well, let's look at what would be the next question. This is also natural for functional analysts, okay? You have a property for larger space. What about some class of subspaces may preserve this property? So the natural class of subspaces is the complemented subspaces of a Banach space, especially because this is a geometric property. So we would like to look at one complemented subspace because you can make a projection not like orthogonal or whatever like that. It should be one complemented. So let X be a Banach space with the Ball covering property. Y is a one complemented subspace. Does Y have the Ball covering property? Actually, in order to solve this problem, we work on the Ball covering properties for operator spaces. So typically it's the B of H, the space of bounding linear operators on a separable Hilbert space. Okay. So this result says that if H is a separable Hilbert space, then B of H actually has the Ball covering property. Okay, this very large space has the Ball covering property. And we also know that just now, capital L infinity fails the Ball covering property. And we also know that capital L infinity is isometrically isomorphic to a one complemented subspace of B of H. Okay, this is the classical result. So this would tell you actually the question for the question is no, because B of H has the Ball covering property, and capital infinity doesn't have the Ball covering property, but it's a one complemented subspace. Actually, this is also completely one complemented, okay, in terms of the operator space language. So, well, okay, just now we said that B of H has the Ball covering property. H, a separable Hilbert space, can be identified as little L2. So the natural extension would be, what about B of LP and B of C0? Okay, indeed, we prove a stronger result in this situation. So let X be a Banach space with X star separable, and for P strictly between 1 and infinity, any subspace of B from X to little LP containing the finite rank operators have the not only the BCP, the uniform BCP, a stronger condition. So any Banach space so that X star is separable and the subspace containing finite rank operators would have the uniform BCP. So as a corollary, we know that every subspace of B of LP containing the finite rank operators has the uniformly bounded, uniformly Bohr covering property. All right, so after we finish the case for B of little LP, okay, of course we want to look at capital LP. However, that's a place where we got stuck. Okay, we got some of the results for a special case, that is the capital L1 case. Okay, the space of bounding linear operators on capital L1 actually fails the Bohr covering property. Okay, using a theorem we proved here. So let X and Y be Banach spaces. If B of XY has the Bohr covering property, then both X star and Y have the Bohr covering property. But you see here, the dual of L1 is L infinity, but L infinity fails the Bohr covering property. So this is a corollary of the theorem here. And then we proved that B of X to L infinity has the Bohr covering property if and only if X star has the Bohr covering property. And if you look at the B of X C0, this is the same. So for X star to have the Bohr covering property. So the corollary for this theorem is the following, okay? So if X is a norm space, then B of L1 to X star has the Bohr covering property if and only if X star has the Bohr covering property. So this would tell you that both B of L1 and B of C0 have the Bohr covering property because in the theorem we just presented P strictly between 1 and infinity, okay? In this case, we cover the 1 case and the infinity case. Okay, and I'm going to finish my talk with 2 open questions. So the first one is this one. So whether the space of bounding linear operators on capital P has the Bohr covering property. So the major difference here, okay, why we got stuck, is because for little LP we have a 1 unconditional basis or 1 symmetric basis. Okay, when you are trying to construct the approximations, the Bohrs, so you do use that property. However, for capital LP, although you have an unconditional basis, the hard basis, however, it's not 1 unconditional. You have the unconditional constant. Okay, but you cannot just do a simple renorming. Of course, you can do a renorming to make it to be a 1 unconditional basis, but since this is a geometric property, after renorming, you might change the property of the original space. So you can't do renorming. You have to directly go through the space. Okay, so this would be I would say, is a very interesting question, but I believe there may be some new approaches may be needed. Okay, and another question is related to what I talked about in the beginning. That is. So for every separable Banach space, it's easy to see it has the Bohr covering property, strong Bohr covering property, and uniformly Bohr covering property. But you can't just say, okay, if the space has the Bohr covering property is separable, certainly this is wrong. But so the right formulation is, if X has the Bohr covering property in every equivalent norm, thus is X separable? Okay, little L infinity is not the case because you have renormings. Okay, make it either with the BCP or not with the BCP. So this is the second question. Okay, the third one I didn't list is the following, because when we look at the direct sum, we only look at the little LP direct sum. You may look at the other different direct sums. For example, we considered Olich direct sums and Lorentz direct sums. But in general, what should be the right formulation is, if you take a 1 unconditional basis, And then you take one unconditional direct sum of Banach spaces, whether the BCP passes from the summand to the summation, okay? So that would be the third question. So this is the end of my talk. Thank you.
Many, many thanks for your interesting many tools. Are other question here or answer?
What is about subspaces of invertible or compact operators?
Okay, so when you talk about say compact operators, what space are you talking about? LP?
Like LP,
For example,
LP small.
For example, for little LP, the answer is already here, right? Because any subspace contains the finite rank operators would have the BCP, right? So for some other spaces, if you say compact operators, I would say, for example, for capital LP case, we don't know, because even for the entire space.
And invertible operators, invertible.
Invertible operators, okay, so this is a good question, but I think
it's quite good
right.
for applications.
We haven't considered invertible operators, okay.
Thank you. Yeah. It's very interesting for applications, for integral equations, for instance, something. Does it relate to some applications, this property? This is quite curious.
So I think when you talk about invertible operators, I would say because you're talking about a set, right? So that's a little bit different.
Considering like open subspace in B, X, Y, for example, like invertible operators, as we know.
Yeah, so whenever you talk
like
about
subspace,
invertible operators, it's not gonna, you can make it like a linear space, so that's in a different setting. Okay, I would say you can consider maybe different subsets, that's possible, but you have to impose the right condition. Because here we're talking about spaces.
Yeah, okay, thank you.
Okay, let me mention your theorem about the CK of X. No? You
yes.
provide that the CK of X as a...
Just a moment, let me go back to the place. Yeah.
Yeah, here. CK of X as BCP, if and only if it's CK, and X as BCP. But you know, you can rewrite the CK of X as an injective tensor product of CK and X. Then it should be natural to ask if you have two Banach spaces with BCP, then injective tensor product still has, or projective, of course.
Yeah, thank you. Actually,
have you thought about that? Or?
Yeah, actually, in that paper, because I didn't write it, for some of the results, we just passed to an injective tensor product to have the characterization go that way to trying to prove the result. Yes, we indeed would consider, but in general, because if you are away from like C of K, or C of K for injective tensor product, or L1 for projective tensor product, then things are much more complicated because those spaces are really very far away from your product, right? So it's not easy. Yeah, in the CK case, we indeed use the injective product.
Okay, but do you think in general, the projective or injective tensor product to Banach spaces with BCP or not?
In general, our guess is difficult because if you just take arbitrary two spaces to take the injective tensor product, that space is huge.
Oh, yeah, of course, it's huge.
It's much larger, so somehow it's very difficult to directly lift the information from the base space to the larger space. Maybe you look at a particular one could work, but that...
Okay, thank you.
The same question about tensor product. It's the same.
I'll say? Okay.
Yes.
Okay, any other question? No? If not,
Paco?
Oh, Paco. Sorry.
Okay, well, what I'm going to ask you, maybe it's on the slides. Can you go back to because you showed a theorem where you prove that summation of xi, like the p summation of xi. Yeah, okay, so sequence, okay. And then after that, you also showed on a slide about hereditariness to one complemented subspaces, right? Hereditariness of like after.
Yeah. After that, we show that it doesn't pass to one complemented subset. But in this case, in LP case, it passes to LP summons.
Okay, that was my question.
It's not a general one complemented case.
Okay.
Like the capital L infinity complemented in B of H, but that complementation is actually internal direct sum.
Okay.
That's different. This is external direct sum.
Okay.
Yeah.
Okay. But can you go back to the one sorry.
So go back or forward?
I don't know exactly where it was. Okay, maybe back.
Back?
Yeah, back or no. I think it was further. Sorry, forward. Okay. Oh, back. Okay. Yeah. That's okay. Okay. And okay, so there's another slide, sorry, about this, the hereditariness. No, this is one direction. I mean the other direction, where you showed that example where the L infinity is isometrically isomorphic to one complemented in a subspace, and then it's not like BCP is not hereditary to. Can you show that slide, please?
Okay.
Sorry.
Let me see.
No, I think it was back.
No, not here. Let me see. Yeah, here, right?
Yes. Okay. I think it's in the previous slide to this one, you posed the question, right? About okay, yeah, question. Yeah, that's the question. So, have you tried? There are stronger one complemented subspaces, like E complemented, or have you tried hereditariness?
You said what complemented?
Capital E complemented is stronger. It implies one complementation and other geometrical properties related to two-dimensional norms and stuff like that.
Okay, so here...
Or in general, any other complementation which is stronger than one complementation.
So in here, I just mentioned a little bit. For example, this capital L infinity is completely one complemented. So that's why in a sense of operator spaces, it's a stronger complementation.
Yeah, it's a stronger complementation.
But still fails. Still fails. So then you want to formulate what is really a stronger complementation.
There are different generalization. Well, there are different complementations which imply one complementation. For example, there's this one complementation, but I don't think that one is going to help. That means that both both the projection and the complementary projection I minus P both are one projections, and there are other generalizations of one complementation that maybe. I mean, my general question is that it may be worth studying, trying that question for stronger definitions of one complementation. Different from completely, different that the counterexample that you provided.
So for this question, I think we've thought about some of the other directions. For example, you may restrict to a certain class of spaces, okay? And certainly you...
and it is still,
you
still
see
fails.
whether you have it. As you said, you may consider at the same time some requirement for the dual space. For example, the complementation, the original one, and the dual space, okay? There could be such a try, but yeah, we haven't really gone very far, but certainly that's one thing we might consider.
Okay, okay. Thank you very much. I'm sorry for...
Maybe it's time for the last talk of this morning session. It will be, we thank the course. First, we thank again the speaker for his very interesting talk. Sorry. And we have... Okay. Okay. Professor Philip Book, could you hear me?
Yeah, can you hear me?
Could you share your screen? Okay.
I'm sharing. Is it?
Because, okay.
Is it sharing or not?
No.
Is it sharing?
Okay.
Hello, can you hear me?
Some
Hello?
problem with the microphone.
Can you hear me? Okay, so can I start? Okay, so can I start? Yeah. Okay. So hello to everyone. Thank you very much to the organizers for this opportunity to present a talk online. So I wish you are having a very nice time in Spain. Okay, so you can hear me? Do you hear me?
Sorry, we have some technical problems for the audio.
Okay, so let me once again let me thank the organizers for this opportunity to present a talk. So I'll be speaking about orthogonal polynomials and
we have some problem with the audio. We don't hear.
But on chat
No.
Someone is writing that you can hear.
Could you wait for a minute?
Yeah, yeah. Is it solved?
Okay. So
Can you hear me?
just wait for a few minutes. I hope that they will fix this problem very soon. So, is it okay already to speak? Yeah. Can you hear me? Okay.
So, is it okay to speak? No, not yet. Okay.
Sorry for this problem. Maybe we have the solution.
So already okay?
The problem is for the audio in the auditorium, but maybe the organizing committee saw these inconvenience, and I hope that in few minutes we can listen Professor from Poland. I hope so. No? Sorry for...
Okay, can you hear me?
Okay, let's start.
So are we starting, yes?
Okay, it's a great pleasure to announce Professor Filipuk from Poland, and her talk, the title of her talk is Orthogonal Polynomial and Painleaf Equations. Please start. Thanks.
Okay, thank you very much, and thank you very much for this opportunity to present a talk online. So I shall just be very brief. So I'll speak about connection between orthogonal polynomials and nonlinear differential equations. So as you know, orthogonal polynomials appear in a wide range of applications in mathematics and mathematical physics. So they satisfy the three-term recurrence relation. And if some weight function depends on the parameters, then also recurrence coefficients and polynomials would also depend on this parameter. So an and bn would be called to the recurrence coefficients, and I would be interested in the behavior of these recurrence coefficients for certain weights. So for monic orthogonal polynomials, we have essentially the same recurrence relation. So well, I mean, the recurrence coefficients would be the same, but the three-term recurrence relation is a little bit different. So let me speak about Painleaf equations. Maybe you are not familiar with them. So this is one of the examples of the Painleaf equation, and this is equation with which I will be dealing here in this talk. So as you can see, this is a second order nonlinear differential equation, very complicated. So in general, it is assumed that this equation is over complex numbers, and also alpha, beta, gamma, and delta here are arbitrary parameters, complex parameters. So those equations were found by Penlevé and his students, and they appear in a wide range of applications in integrable systems, in random matrix theory, and in many, many areas. And sometimes recurrence coefficients for certain weights are related to some Penlevé equations. There are 6 Penlevé equations. They are reducible, and sometimes they're called nonlinear special equations or transcendence. Solutions are called Penlevé transcendence. So usually, if you use the technique of ladder operators for orthogonal polynomials, and also combine with some kind of Toda type differential different systems, so sometimes you are able to see that the recurrence coefficients satisfy this Penlevé equations. So sometimes discrete, sometimes also differential. But usually those equations for the recurrence coefficients, of course, they are not immediately Penlevé equations. So one needs to identify with the canonical form. And this is a very difficult problem. and this is called the Penlevé identification problem. And actually, those equations have very, very nice geometry. So this was studied by Okamoto. And he proposed a kind of a very interesting notion of a space of initial conditions. So I'll just explain in a second what this means. So on this space of initial conditions, Penlevé equations or Hamiltonian systems equivalent to them become regular. And this space of initial conditions can be very nice. It can have some symplectic form. And actually, this space includes a lot of information about differential equations and symmetries. So let's have a look at this example. So this is the deformed Laguerre weight, which was studied by Min and Chen. And this is given by this weight. So as you can see here, this part is just the usual Laguerre weight, but here we have some deformation. So theta is a Heaviside function. So certain auxiliary functions Rn and Rn small, which come from the ladder operators, satisfy the following, so are related to recurrence coefficients by this formula. So essentially they are recurrence coefficients, but a little bit kind of shifted. And auxiliary functions satisfy this second order differential equation. So although in the paper of Min Chen, they already kind of found the connection to the fifth Penlevé equation, it is kind of, it was interesting for me to have a look at this system from the point of view of kind of regularization of this system and from the point of view of the space of initial conditions of Okamoto. So let us give some very few details about what I do. So this is okay. So I'm going to use a certain notion from algebraic geometry. So this so algebraic geometry notion is a notion of blow up. So you consider your initial system in Q and P coordinates, but then you can compactify your space, and now you are considering your space like projective space. So you're introducing also those coordinates. And so since solutions of the Penlevé equations are meromorphic, so we want also to understand what is happening at infinity. So we rewrite our system in new charts. And if we see that the right-hand side becomes 0 over 0, so we need to resolve this kind of indeterminacy. And resolution of such points so geometrically, this is just inserting a projective line over a point, but algebraically, this is just a change of coordinates. So we're introducing, instead of, say, coordinates xy, we're introducing two new charts, uv and uv big. And again, see what is happening with our new systems, whether they have any other points of indeterminacy. Okay, so let's have a look at what we have. So if, for instance, if we, for instance, we return back to the system, then we will see that. So, for instance, okay, so if I'm introducing now Rn and I'm replacing Rn by Q and Rn by P. So, so first you you would be able to see 4 initial points of indeterminacy, and also you will see the 5th point in some kind of infinity chart. So the first points of indeterminacy can be resolved just after one blow up, and the final chart systems regularize. So in other words, as you can see here, if you substitute V capital is 0, then the right-hand side already doesn't have any further points of indeterminacy on the exceptional divisor. And also you can see that the form of the system is kind of very similar. Also the same is happening when you resolve the third and the 4th point. And actually here you see that just applying very, very easy transformation, Möbius transformation, you'll just get the 5th Penlevy equation, which was given here, if you remember. So this Penlevy equation for the function u with certain values of the parameters. And this is the same for all charts. The resolution, if you remember, there was a 5th point. So the resolution of the 5th point is a little bit more complicated, and you need several consecutive blow-ups. So you first see this point, then again you see this point, and so on and so forth. So in general, this process for differential equations may not terminate, but for Penlevy equations, somehow this is almost always finite. Okay, so and also there is some intermediate local transformation which I do, which is due also to Takana. So this is some local change of variables, and the final system finally looks like this. And if you compare the structure of the system again with, say, with these systems, then you again see similarity. So therefore, just using a very, very similar Möbius transformation, you again get the 5th Penlevy equation for these parameters. Okay, so so from your initial system QP, you use this birational transformation in order to get this system, and the inverse transformation is also given here. So we also have certain Riccati type solutions for these special values of the parameters of the 5th Penlevy equation. So it means that we're dealing with the so-called classical solutions of the 5th Penlevy equation. Now, if you take our 5th Penlevy equation and you are taking this replace, so you replace t independent variable by s using this kind of transformation, and you're considering what is happening at infinity as n tends to infinity. Then you'll see that the first coefficient here in this kind of formal expansion with respect to n satisfies satisfies the so-called Penlevy 34th equation. And also, what we also so here, as you can see, so all those final chart systems are rational in general. But now the question is like you started from. Is it possible kind of to regularize the system and find some systems with polynomial right-hand sides? And also, if the systems are with polynomial right-hand sides, you might ask very easily if the system is Hamiltonian or not. So one more blow-up would give you the polynomial right-hand sides, and also you can check that those systems would be Hamiltonian with such nice Hamiltonian functions. So and then you can pull back and recalculate that also those systems here would and here would also be Hamiltonian with a little bit different kind of symplectic form, and they can be written down in this way. Of course, if you're just looking at this system, you cannot very easily tell whether the system is Hamiltonian or not. And using this kind of geometric approach, you easily can write those systems in this way. And the same is happening for H2, H3, and so on. So here I've given just explicitly those examples of the Hamiltonian functions and corresponding systems. So here H8 Hamiltonian is a little bit, as you can see here, is a little bit longer. So LaTeX even kind of cut the formulas. So yeah, and the initial system is also, so if you trace back all the transformations, all those birational transformations, you'll see that also your initial system is also Hamiltonian with respect to this form. So just have a look at this system, have a look at this initial system. So Rn big is Q, Rn small is P. So of course you cannot tell just immediately from the system that it can be written in such a nice way. So in other words, we have proved that the initial and final Church differential systems can be written as Hamiltonian systems. And now, just one more problem is that, so we have the so-called back-on transformations of the fifth Spelling equation. So it means that we know, if we know some solution with certain values of the parameters, we can find another function. So this is written in this way, which gives again solution of the fifth Spelling equation with new values of the parameters. So in other words, you know how to generate new solutions of the Pavlov equation, given if you know some initial seed solution. And actually, if you change the parameters n to n plus 1, then you'll see that the new solution would satisfy kind of this formula, and from this formula, it's very easy to find this kind of discrete system. So this is known as some one of the Pavlov equations, discrete Pavlov equations, and so in the theory of Pavlov equations, discrete equations are also very studied in in some details. So yeah, so this just gave you information how to transform, so how to get the system if you know those kind of final chart systems. Yeah, so what I wanted to say is that this kind of combination of orthogonal polynomials of differential equations, so this procedure of blow up and from algebraic geometry and regularization sometimes gives you very nice results, and in particular it allows you to solve the so-called a Pelevy equivalence problem. So, so how to identify your given system for the recurrence coefficients with one of the Pelevy equations, and also as a kind of in addition, you get very nice kind of Hamiltonian formulation, and once you know the fifth Pelevy, the recurrence coefficients are related to the Pelevy equations, and then you know how to construct also some discrete systems for the recurrence coefficients. So basically, this is it. So thank you very much for your attention. So are there any questions or comments? Thank you.
Are any questions? We try and interact. There are no questions. Okay, thanks again.
So thank you very much, and enjoy the conference. So, see you at some point somewhere.
Could you repeat? Okay, we say bye.
Bye.
And we thanks again.
Thank you. Thank you.
Okay, thanks again to Ben, Anna, and Nina and Marina for this session. It is closed, officially closed. Okay, thanks.